This is 7.2 example 6. We have the integral from 0 to pi over 4 of tangent to the third power times secant to the third power. So far the examples I've done have all had sine and cosine in them, and so we have some new trig functions on the scene. We have tangent and secant, and so the same idea as before. We're going to play this little game as we did at sines and cosines, but a little bit different rules or variation of that game with regards to the odd even powers. And this has to do with the derivative of each of those trig functions. So recall that the derivative of tangent is secant squared, and also the derivative of secant is secant tangent. So if you look at the integration strategy handout, this is case 3i b double I little i's, and so here this tells you that the power of tangent is odd, and that's what we're going to go with here. The other options don't apply. So this looks like a good way to proceed, and just speaking to that again, secant is even is the case lowercase I, which is clearly not what we have here. The other category, which is the 3 lowercase i's, is kind of more kind of like if the first two don't apply. So this is somewhat in ranked order with 1 and 2 applying first. Anyway, this is the case where tangent, the power of tangent is odd. So you'll see how that comes into play, and it has to do with our derivative of that function and whether we have that part of the du present there that we can handle in a good way, with the leftovers being taken care of by a trig identity. So let's get going here instead of just talking about it. Because we're in this case, we're going to let u equals secant theta, and one of the first things, just kidding, secant x. And so one of the first things we're going to do is we're going to take the derivative of that to find the du. So just kind of reviewing that again, take the derivative of u with respect to x, and what we get is secant of x tangent of x. And then that's how we get our cute little equation for du. We multiply both sides by dx. So we have secant x tangent x and dx. Alright, so next thing is we should be able to save a factor of secant x tangent x from this, and then good things should happen. So go back to our integral with that in mind, and let's rewrite it so that we are going to take out a tangent. So I'm going to do it this way. I'm going to write tangent squared times secant squared, and then put my additional tangent and secant at the end here. So an equivalent way to write this integral so that I can have my du identified as secant tangent or tangent secant, however you want to write that. And then now we need to start handling the rest of this. Our u is equal to secant of x. So what we're going to have here is u squared for the secant squared. No big deal. And then typically we have some leftovers. Because we had the power of tangent being odd, that implied with our u sub here being secant, when we take the derivative, there's going to be a tangent present in that du that's accounted for. So we separated that, which makes the leftovers of the power of tangent being even. And so that's what's going to work to our advantage here, because we have an identity that has to do with when tangent is squared. So the identities that you need to memorize from this section again are the two Pythagorean identities. So I'm kind of getting ahead of myself. Let me write down a few things that I was saying. So leftovers, we need to use the u, which is secant of x, which which seems bizarre, again, because it's tangent, but this is where the motivation for the identity comes in. Alright, so again, the two that you need to memorize, two identities, are Pythagorean identities. So sine squared plus cosine squared equals 1, and the other one is secant squared minus tangent squared is equal to 1. So if you memorize that, then you can compare with what we have. We have tangent squared, and we're trying to put that in terms of secant. So we just solve for tangent squared. Different ways to do that. I'm just going to add it to both sides here and then subtract 1 in a flash here. So then I'm going to have secant squared minus 1 is equal to tangent squared. So what we're going to do is we're going to plug in secant squared minus 1 for tangent squared. Then we can use the u for that, because what we'll have then is u squared. So we're ready to put all that together. We're going to go ahead and do that. Because I'm starting to write things in terms of u, technically I need to change my limits of integration, or the little numbers next to the integral sign. So a way to kind of do this in a legit way with a notation is to just write g of those numbers, because remember u is equal to g of x, so it's just a way of saying, hey, yeah, I got to put these in terms of u, and that would make sense. And now what we have is u squared minus 1 times u squared times du. And hopefully now we have an integral that is easy to evaluate. We have just a tad bit of simplifying to do, nothing major, by distributing the u squared. And so what we have is u to the 4th minus u squared. Evaluate that integral, and what you'll get is 1/5 u to the 5th minus 1/3 u to the 3rd. And then you got to plug in so somewhere along the line here you have to make a choice on how you're going to sub in. If you want to leave this in terms of u and not go back to your original x, then what you need to do is actually find g of 0 and g of pi over 4, because those are u values. This is like u1 and u2 or something. Alright, so your g of x is the u, which is secant. So u is equal to g of x, which is equal to secant of x. So you just plug in there. I need a little bit of room, so I'm actually going to go all the way over here to the left and start doing that. So I'm going to actually grab this, bring it over. So g of 0 is secant of 0. If you got that just off top of your head, congratulations. I always like to go back into terms of cosines and sines. It's just easier for me to do. So cosine of 0, I know that is 1 off the top of my head, so I know that secant of 0 is 1. So that means when I can go back here and plug in 1, and this will be in terms of u. So I need to find the other one. The other one was g of pi over 4. So I'm finding secant of pi over 4. So I'm going to do this in the same style. I'm going to find the cosine of pi over 4, because that's easier for me to do. It's the square root of 2 over 2. And so I can write that as 2 over the square root of 2, which isn't simplified, but you know, maybe we'd have to do some simplifying elsewhere. So I'm just going to leave it as b, as it is here. Alright, other things. It's good enough for now. Alright. Alright, now I'm going to plug in for u. So I have 1/5 times first plugging in 2 over the square root of 2 to the 5th power minus 1/3 2 over square root of 2 3rd power. So that's plugging in 2 over the square root of 2. I'm going to minus, need some grouping symbols, and I'm plugging in 1 for u. So 1/5 times 1 to the 5th minus 1/3 times 1 to the 3rd. So next, we're going to have 2 to the 5th. And I'm just noticing now that maybe I should simplify this first, and that's actually going to make this easier. So I'm a little more motivated now. 2 over the square root of 2, whenever you have a square root of 2 in the denominator, like a square root in the denominator, it's not considered simplified. So I just noticed when I make this to the 5th power down low, it's not going to go away. So if I just kind of handle it here, the way that you simplify it is you multiply by, in this case, square root of 2 over 2. So I'm actually just going to do that conversion within here. I probably should have done it before. Not have been so lazy, but oh well. That means I have to write down twice. No biggie. Alright, next thing is easy. 1/5 plus 1/3. No repercussions there. Okay, next thing, I'm still working on the simplifying. So what I can see here is I have 2 times the square root of 2 on top. Square root of 2 times square root of 2 is actually 2, so that's what happens, is all we have is square root of 2. And that's way easier to deal with here. Okay, same business here. We're going to have square root of 2, and that simplifies to just the 3rd power now. Okay, next I guess I can put together minus 1/5 plus 1/3. Get a common denominator, multiply by 3 over 3, so I get minus 3/15 plus 5/15. Getting ready for that. Now, we have square root of 2 to the 5th power. So a couple ways to handle that. Let's show a little bit more work here. You can bring the 5th power down low, or not down low, but into the root. And so you can think of this as 2 to the 5th under the root, which I'm going to write as 2 to the 4th times 2. And that's going to simplify in the next step. Okay, 1/3, same type of thing here, square root of 2 squared times 2 is equivalent to 2 to the 3rd inside that root. Here we get plus 2/15. Alright, next we have 2 squared, which is 4 for the first part, times square root of 2. So that's simplified. And we got minus 1/3 times 2 square root of 2 plus 2/15. Okay, now these are kind of like terms here in a sense that I got square root of 2's in both of them. Got a denominator of 5 and 3, so 15's common denominator again. So I'm going to handle that. I'm going to get, for the first here, we have 4/5, and so then we're going to multiply by 3 on the top and the bottom, 12/15 times square root of 2, minus, here we're going to multiply by 5 over 5, 5/15, except I forgot the 2, so this is 10/15. Square root of 2, we're getting there. Okay, 12/15 square root of 2 minus 10/15 square root of 2. They're like terms, the square root of 2 being the common thing, or you can factor out however you want to think about it, but you get down to 2/15 square root of 2, combining them, plus 2 over square root of 15, which you can call it a day right here for you really precise people that want to write this all the way simplified. Technically you'd write it that way, but and that's it.